Okay, here's just a little information on how to work problems with direct variation. So first, let's just look at a table and see what direct variation looks like. So the x column, it increases by 1 each time. The y column increases by 3. So to check if it's direct variation, I want you to think is it proportional? So if you compare any two sets of numbers, the x's and the y's, you'll notice that they're proportional. So 2/3 is the same thing as 6/9. So here's the idea. Y is equal to something times x. When I say something, I'm just going to use the variable k to represent that something so I don't have to keep saying that. So it should have the form y equals kx. That something in this case is 3, because if you multiply 3 by each of the x's, you should get the y value. So you might be asking, is every linear equation here a direct variation? Well, if you ask it if every linear equation is direct variation, I would tell you, nope, not exactly. Let's compare two examples. So the first one, which is that example of direct variation we saw, again, the slope of this equation, we talked about slope before, is 3/1. The y is changed by 3, the x is changed by 1. Well, here's another, the table on the right, the slope is still 3/1, or you could just say the slope is 3. But the equation on the left, I can represent with the equation y equals 3 times x, and it works for every value of x. But if I try to find some fixed value that you multiply the x by to get the y, you'll notice that 1 times 5 is 5, but then, wait, 2 times 4 is 8, and then 3 times, I have no idea, is equal to 11. But no fixed k that you multiply the x by will give you the y values. This equation that represents this one is actually y equals 3x plus 2. But we're not going to focus on that. Those are we'll talk about later. We don't want to focus on how to write the equations of non-direct variations. Let's just focus on how to write the equations of direct variations, which are in the form of y equal kx. So if you're told that two variables vary directly, you're able to represent them in the form y equals kx. So in place of y, I'm going to put what my y value is. And in place of x, I'm going to put what the x value is. And if they do vary directly, that means you multiply x by something to get the y. So I'm going to solve for the k in this equation. So I get k equals -2, which means y equals -2x is the direct variation that represents these. So what if you were told that, well, find the y when x is equal to, say, 3? You just plug in 3 into that equation. If they said find the y when x is 14, you just plug 14 into the x of that equation. You could do this with infinitely many different values. These are just two examples of ones you could find. So let's look at another example. Again, let's look at some tables. Let's see if we can check just by looking at the tables if these are direct variation. The idea is that if we divide each y by the corresponding x, we should get the same value or the same slope each time, if you think of it that way. So in this case, when we divide each y by their corresponding x, you get -4. I'm just going to plot these just to show you what the graph of those look like. So the 2 matches up with -8. The 3 matches up with -12. So I'll plot those. And if you actually go backwards a bit, you'll notice that 1 would match up with -4. 0 would match up with 0. And just to see overall all the points, I can even plot these in Desmos and generate a table using Desmos to plot the points a little cleaner than doing it by hand, even though I was able to do it by hand. But you'll notice that it went through the origin right there. And I'll look more at that graph later. So this second one, you might think, well, this can't be a direct variation because the x's and the y's change by different amounts. But here's what's important. The y divided by the x is going to be the same number each time. If I take the 4 and divide it by 2, I'm going to get 2. If I take the 10 and divide it by 5, I get 2. 20 divided by 10 is 2. 80 divided by 40 is 2. So all that matters is that there's some number that you multiply the x by to get the y. Again, I can plot that variation by hand here, and here I can do a little one-to-one scale. So 2 matches up with 4, 4 would match up with 8, 100 would match up with 200. But the idea is whatever the x is, you double it to get the y, and that's a direct variation. So I can modify my equation here in Desmos, and all of those points that I want can match up here. I can even plug in these other x values into the table just to confirm that those values from the table, x values, match up to the corresponding y values. All right, let's look at one more. And this is going to be an example of one that is not direct variation. And here's how you can tell. If I divide the y by the x, each time I divide the y by the x, I get a different potential k value or a different slope. But really, that's not the slope of this equation. All this means is that this thing is not proportional. In fact, this is still a linear equation. If I were to plot these points, perfect line right here. I can plot a perfect line between these two, but you'll notice that the direct variations, they will go perfectly through the origin, whereas this one right here, if I plotted it, it wouldn't go through the origin. But look at the slope. If I show the change in y over change in x, whether I call it 20 over 4 or 5 over 1, the slope of this is 5. Now, the difference between a direct variation and other linear equations that are not direct variation is that I have to change the y-intercept. And we'll talk more about that later on. But you notice if I make the equation y equal 5x minus 3, it happens to work out for the values that I care about. And something interesting we'll talk about much later is that negative 3 is the value right here. And here's a little something for your viewing pleasure to think about.
What are you doing? You think you're funny?